Welcome to the Deep Dive, the place where we take these huge stacks of technical documents and really just boil them down into pure, high-value knowledge.
Yeah, get right to the good stuff.
Exactly. And today, we are strapping in for a really high-speed journey into the essential mechanics of metal removal. We are talking about mastering milling, the fundamental theory, the strategic setup, and all the complex calculations that govern it.
It's a huge topic, and it's changed so much.
It really has. I mean, if you still think of milling as just a way to, shave flat faces off a block of metal, you really need to update your software.
Absolutely. Thanks to massive advancements in, well, in everything, CNC architecture, multi-axis capabilities, sophisticated CAM programs, milling is now a truly universal machining method.
It's making these incredibly complex forms, intricate surfaces, holes, cavities, things that were just impossible a generation ago.
And that universality is, I think, exactly why we need this deep dive. You, our listener, you sent over this just exhaustive technical stack. I mean, it outlines everything from foundational chip theory all the way to advanced tool selection.
So our mission today is to take that technical manual, all the definitions, the formulas, the non-negotiable rules, and transform it into practical, high-value insights.
Yeah, this isn't just theory for theory's sake. This is the essential roadmap you need to succeed on the machine floor, especially when productivity and, precision are everything.
So let's frame this a bit. Why does understanding these deep fundamentals, why does it matter more now than ever? I mean, we have these incredible automated CNCs. Why do we still have to get bogged down in the basic physics?
That's a great question. And it's because of the shift toward efficiency through flexibility. Modern manufacturing relies so heavily on these sophisticated CNC machines and, crucially, on multitask machines, the turn mills.
Right, the machines that do everything in one setup.
Exactly. And combining operations saves a massive amount of time, but, and this is the key, it introduces some severe physical constraints that, a dedicated machine just didn't have to face.
What kind of constraints?
Well, for one, you often have reduced overall system stability. You're almost always dealing with significantly longer tool lengths because of turret or magazine constraints.
Ah, the dreaded long overhang.
The dreaded overhang. And as a result, you might be forced into a lower depth of cut, your app. So these fundamental principles, how to calculate power, how to position the cutter, how to choose the right insert geometry, they become the exact tools you need to manage those trade-offs effectively. It's how you maximize your metal removal rate and really how you conquer the stability challenges that are just inherent in this universal machinery.
Okay, let's unpack this then. We have to start with the foundational language of the cut. I feel like if we miss the interdependence of these first few metrics, all the advanced math we get into later as well, it's kind of meaningless.
It is. It all builds on itself.
So let's start with speed. Specifically, how rotation translates into actual physical cutting action.
Okay. The first, most visible metric is spindle speed, which is noted as N.
Simple enough. That's the revolutions per minute, the RPM of the tool on the spindle is what you punch into the control.
It is. It's our primary input lever.
Yeah.
However, the real physics, the thing that's actually happening at the cutting edge, that's the cutting speed, VC, or sometimes V.
And VC is the surface speed. So it's typically measured in meters per minute or feet per minute in the U.S. It's the metric that tells us the actual speed at which that cutting edge is engaging the workpiece material.
Precisely. And what's so crucial for a planner or an operator to internalize is the interdependence that's created by the tool's geometry.
What do you mean?
Well, if you fix your material's required VC, which you're getting from material handbooks and, based on the tool life you want, and you select a tool with a specific cutter diameter, DC, then the spindle speed N is, it's no longer negotiable. It's a result.
It's just math at that point.
It's just math. The formula, VC equals E DCAN 1000, it shows us that the larger the cutter diameter, the slower the spindle has to spin to maintain that optimal VC.
So it's this constant balancing act. Tool size versus the materials requirement. And getting that right is essential for ensuring your insert is actually cutting, not just, rubbing or overheating.
Exactly. That's the foundation of everything.
Okay, so moving from speed to movement, let's talk about feed, because this is really the engine of productivity. We need to clarify three related terms here, starting with the theoretical input. Feed per tooth.
Right, SSC. It's measured in millimeters or inches per tooth, and it's a calculated theoretical value. It's derived directly from the recommended maximum chip thickness that the insert geometry and the material can safely handle.
So it's the goal. It's what we want each cutting edge to remove.
It's the goal, yes. But what the machine actually moves is the table feed, VS, or, feed per minute.
And VF is the programmed movement rate of the tool relative to the workpiece in distance per time, like Emin. So if Z is the theoretical quality requirement, VF is the practical productivity outcome.
Perfect way to put it.
But how do we bridge those two? There's a missing link.
There is, and it's knowing exactly how many teeth are participating in the cut.
Okay.
So the total number of available cutter teeth is ZAM. If you look at a milling cutter, that's simply the total number of inserts it holds. Easy.
But that's not always the number you use in the calculation.
Right, and this is what often confuses new planners. You don't always use ZN, you use ZC, the effective number of teeth.
Okay, let's really focus on that ZC. What dictates the difference between the total number of teeth, ZN, and the effective number, ZSE?
It's dynamic, and it's dictated entirely by the radial width of cut, AE.
Okay.
So if you're performing a full slotting operation, meaning the entire tool diameter is engaged, A equals DC, then ZC equals ZN. Every tooth is engaged for a big part of the revolution.
Exactly.
However, in, say, light face milling or high-speed side milling, where your E might be very small compared to DC, only a fraction of the available teeth might actually be in contact with the workpiece at any given moment.
So in that case, ZC would be significantly less than ZN.
Significantly, and that distinction is absolutely crucial.
Because if I mistakenly use ZN in my calculation when only, say, half the teeth are engaged, I'm essentially doubling my calculated feed rate. I'd be overloading the actual cutting edges.
And that leads directly to chatter, or worse, tool failure.
Right.
Precisely. So this brings us back to that foundational formula we mentioned. The practical machine motion, VF, is directly proportional to the theoretical chip size FSC, the rotational speed N, and the number of teeth actually engaged, ZSC. So VF SEEC, ZSCN.
And that relationship is basically the master key. It's how you convert the materials requirement, the SC, into safe, productive machine movement, the VF.
That's it. You've got it.
Okay, so now that we have the speed and the movement figured out, we need to quantify how much metal we're actually removing. And we define the dimension of that chip cross-section with AP and A.
Exactly. So AP is the axial depth of cut. This is simply how much the tool is set below the unmachined surface, the depth of your face cut. AC is the radial cutting width. It's often called the working engagement, which is the width of the component engaged by the cutter diameter. And those two dimensions, AP and A, they define the raw volume of material that's being attacked by the tool.
As soon as we define that volume, we have to start talking about the energy needed to shear it off. This brings in power and torque, and this is where those machine constraints we mentioned right at the start become so critical.
They really do. So PC is the net power. This is the power the machine must be able to supply to the cutting edges. It's the required horsepower to achieve your desired metal removal rate, which we call Q.
And you have to factor in the machine's own efficiency, right?
Always. You must. A machine's efficiency is typically around 80% to 90%, so if I have to factor that in when you're selecting your cutting data to make sure the machine can actually deliver that PC.
So if your required PC exceeds what the machine can actually deliver, you've got a problem.
You've got a problem. And you have two choices. Reduce your VF or reduce your chip cross-section, the AP times A. There's no other way.
And power translates directly into metane, or torque, which is the rotational force. So the machine could supply the power, but if it's at a low RPM, it might not have the torque, and the spindle could chatter or just stall out.
Absolutely. And the calculation for both PC and Mikaya hinges entirely on one critical value, Kc, the specific cutting force.
Okay, Vicky.
This is a material constant. It's measured in newtons per square millimeter or pounds per square inch. And this constant represents the material's own resistance to being deformed and sheared.
This NACE value feels like the sort of the invisible anchor point of this whole system. What does a planner actually do with a value like, say, 1700 Nm Picano for a basic unalloyed steel?
That 8C value tells you the pressure required to cut a single square millimeter of chip area. So if you know your machine's required PC is, say, 15 kilowatts, and you know your material's Kc is really hot, like a tough high-temperature alloy, that high Kc value is going to force you to severely restrict your chip cross-section, your AP times A, and your feed rate, your VFF, just to stay under that 15 kilowatt limit.
But on the flip side...
If you have a material with a low AC, like aluminum, you can be really aggressive. You can increase AP and A, maximize your metal removal rate, because the material just offers very low resistance.
So the Neki constant is really the indispensable link. It connects the material's physics directly to the machine's electrical capacity.
It is the bridge between the material and the machine.
Okay, so we've covered the language of speed, movement, and power. That's a lot already. Now we need to transition from that energy physics to the geometric physics of the cut.
Right. Strategy.
This next part is all about the strategic choices that really determine success or failure on the shop floor. We're talking about the direction and the positioning of the cutter. And the source material makes one rule incredibly clear: the absolute supremacy of climb milling.
Yeah, this is non-negotiable. So you have two methods: conventional milling or up milling, and climb milling or down milling. The source material explicitly demands always use climb milling for best cutting conditions.
Always.
Always. It's all about how the chip is formed.
Okay, let's visualize that chip formation. What is the microscopic difference that makes conventional milling so detrimental?
So think about conventional milling. The insert is moving against the direction of the feed. So it starts its cut at 0 chip thickness. It literally rubs the surface for a moment, and then it progressively increases the chip thickness until it finally exits.
That sounds inefficient.
It's terrible. That initial rubbing action, starting at 0 thickness, it generates a massive amount of friction and heat immediately, and this causes what we call the burnishing effect. It literally polishes the surface instead of cutting it cleanly.
And it can cause work hardening of the surface,
Yeah.
right? Which would make the next pass even harder to cut.
Exactly. It's an incredibly stressful process for the insert tip. You get reduced tool life, a poor surface finish. It's just bad all around.
So how does climb milling completely reverse that physics?
In climb milling, the tool rotates with the feed direction. So the insert enters the cut where the chip thickness is already at its maximum.
Okay.
It immediately gets under the material and shears it off. Then it gradually decreases the chip thickness to 0 at the exit. So friction is minimized at the entry, heat is reduced, that burnishing effect is totally avoided, and the cutting forces are stable and consistent throughout the whole arc of engagement. It's just a cleaner, cooler, and faster process.
I understand the preference for climb milling, but is there any scenario where you would ever need to use conventional milling?
I mean, very, very rarely. And usually only when you're dealing with extremely tough surface scale on, say, old castings or forgings where you need to kind of force the chip out differently. But for modern CNC work and for overall productivity, climb milling is the rule. And I go further. If a setup isn't stable enough for climb milling, the planner needs to reevaluate the entire setup, not just switch to conventional milling as a quick fix.
Yeah, that's a great point. Fix the problem, don't just work around it.
Right.
Okay, so moving beyond direction, let's focus on geometry. The relative size and positioning of the cutter diameter, DC, versus the width of the cut. This is a critical strategic choice, and I think it's often overlooked in the rush to just get the program running.
It really is. So first, the basic selection guideline, the cutter diameter rule. The cutter diameter DC should be about 20 to 40% larger than the width of cut, AB.
So you need the tool to be offset from the center of the workpiece.
You must. And the source provides this great practical example, the 23 rule.
Okay, let's ground that rule in reality. Why is that offset so essential? What's it actually doing?
The offset, for example, running a 150 millimeter cutter so that about 100 millimeters is engaged and 50 is out of the cut. It's done purely to manipulate the direction and the consistency of the cutting forces.
So it's about force management.
It's all about force management. If the tool is perfectly centered, the forces shift dramatically as the tool passes the center, and that causes vibration. Moving it off-center obtains a much more constant and favorable direction of forces throughout the entire engagement.
Okay, let's analyze the 3 contact phases: entrance, arc of engagement, and exit based on this positioning. Start with the position we absolutely must avoid at all costs.
That would be the most unstable scenario possible when the center line is directly on the edge of the workpiece. So AE is exactly 50% of DC.
Why is that the worst?
When the tool is centered right on that edge, the radial forces fluctuate violently from positive to negative. You get maximum shock loads at both entry and exit. It is a recipe for maximizing instability and minimizing insert life. It's a hard stop. It is absolutely not recommended.
Okay, so that's out.
Yeah.
Then we have the barely skimming scenario.
Right. Where the center line is well outside the cut, with A being less than 25% of DC, the angle of entry is positive, which is better. The initial impact is taken by the outermost tip of the insert, which can handle it, but the cut is still heavily skewed to one side, and that puts a lot of side load on the spindle bearing, especially on older, less rigid machines.
So better, but not ideal.
Mm-hmm.
Which brings us to the most strategic choice, the most favorable cutting condition.
And that's when the center line is well inside the workpiece, meaning A is greater than 75% of DC. This is the ideal.
And why is that?
By offsetting the cutter deep inside the cut, the initial impact at the cut entry is taken up further along the robust cutting edge, away from that sensitive, fragile tip radius.
Ah, so you're protecting the weakest part of the insert.
You are, and that massively reduces the chance of edge chipping. And crucially, because the exit is also gradual, the risk of chipping the insert as it leaves the material is also minimized. This strategic offsetting is just a fundamental technique for stability and for maximizing insert life, especially in roughing operations.
We've established the strategic rules of the road. Now let's pivot to the application, how we actually select the hardware to execute this strategy.
Yeah.
The source organizes this into a five-step production planning process that really emphasizes working within the limitations of the machine you have.
Right. The planning process is a hierarchical decision tree. You can't just go pick the fastest tool off the shelf. You have to check your constraints first. So step one is the component.
Mm.
What's the material, the geometry, the surface quality you need?
And step two, and maybe the most constraining step, is the machine parameters.
Absolutely.
Let's spend a moment on those machine parameters, especially in the context of these modern multitasking machines.
Okay. Well, the stability of the machine, its age, its available power, that PC limit, and the spindle size, ISO 40 versus ISO 50, those are the obvious constraints.
Right.
But for multitask machines, the critical constraint is often the tool holder interface, and as we mentioned before, tool overhang. Long overhangs are just unavoidable in some of these turret setups, and that instantly reduces the rigidity of the entire system.
And that reduced rigidity then dictates everything that follows.
It dictates step three, the choice of tool, like the pitch and insert geometry, and it dictates step four, how to apply it, so you're cutting data. If you have a long overhang, you simply cannot select an extra close pitch cutter, regardless of how much power your spindle has. The physics won't allow it.
So the machine's own geometric limitations really determine the theoretical cutting inputs you can even consider.
Absolutely. And the final step is, of course, troubleshooting, which is simply applying remedies when the constraints we just discussed, vibration, heat, power limits, cause the planned operation to fail. It's a complete integrated process from start to finish.
Okay, so let's look at the three most common general-purpose cutters for face milling and shoulder work. Let's contrast their advantages and the strategic trade-offs they represent.
Great. Starting with the 45-degree face mill. This is the general, go-to choice for most people.
Why is that?
The 45-degree angle means the cutting forces are balanced. They're roughly equal in the axial direction, so downward into the spindle, and the radial direction, sideways. This balanced force distribution is what contributes to stability and allows for a really smooth entry into the cut. It's just great for roughing and general face work.
Then you have the 90-degree square shoulder face mill, which seems to offer a lot more versatility.
It does, primarily because it can generate a true 90-degree shoulder, which is often a required feature in component geometry. But its major technical advantage is its extremely low axial cutting forces.
And why is that important?
Well, since the force vector is mostly radial pushing the part sideways rather than downward, it's ideal for machining thin workpieces, where excessive downward axial force would cause the part to deflect or would require incredibly expensive heavy-duty fixturing to hold it down.
But the trade-off is that its maximum depth of cut is limited, isn't it?
Yes, very much so. It's typically limited to the length of the insert's edge, which is often just 6 to 10 millimeters. So you gain that versatility and a low axial load, but you lose out on maximum stock removal in a single pass. It's a very clear trade-off.
And finally, we have cutters that use round inserts.
Round inserts are the definition of robustness. They are incredibly strong, very versatile for both face milling and profiling. They really excel when you're dealing with uneven surfaces or, really severe conditions.
But their major drawback relates back to stability.
It does. The round geometry means the cutting force is less directional and more complex compared to the precise angles of the 45 or 90-degree mills. This complexity of forces demands a much higher stability machine. You often need a robust ISO 40 or really an ISO 50 spindle to run them successfully at high feed rates.
So the planner has a very calculated choice to make. If you're cutting a thin aluminum plate on a little ISO 30 machine, the 90-degree mill is the safest bet because of that low axial force.
Right.
But if you're hogging huge amounts of steel on a massive ISO 50 machining center, the round insert mill is the way to maximize productivity as long as you can manage those complex forces.
Exactly. It's always that trade-off. Versatility and low stability requirements with the 90-degree, versus maximum productivity and high stability requirements with the round inserts.
This technical matrix really shows that while milling is specialized, the flexibility of the machines is making it universal. Let's look at how the evolution of 4- and 5-axis machines has just radically altered the landscape.
The change is phenomenal. I mean, multi-axis capability allows for these complex operations like deep hole creation or contouring that used to be strictly categorized as either turning or drilling. The line between the process types it's blurring very rapidly.
The source lists a whole variety of modern methods that really demonstrate this blurring. We're talking about specialized techniques like shoulder milling and groove milling, which are extensions of basic face milling, but then you get into the truly advanced cam-driven methods.
Right. Things like trochoidal milling, which uses these circular movements for efficient deep slot creation, maximizing chip evacuation, or helical interpolation to bore precise holes using a circular milling motion. And then, of course, circular milling for creating bore features. But the absolute peak of this convergence is turn milling.
Turn milling, the ultimate representation of that multitask constraint we talked about.
It is. Turn milling involves using a milling cutter on a machining center to perform what is essentially a turning operation on a static workpiece, or, vice versa.
Which means fewer setups and huge time savings.
Huge time savings. But now the planner has to manage the constraints of a non-dedicated machine. The tool's often longer, the rigidity is lower, and the planning complexity, just managing the kinematic relationship between rotation and feed it, drastically increases.
And this is why knowing the foundational physics of power and stability is completely non-negotiable for the modern planner.
That's it. They're not just programmers anymore. They are dynamic stability engineers.
We are now diving into the single most influential component in the entire system, the insert itself. This little piece of carbide or ceramic, it dictates everything: performance, finish, tool life. Let's look at the insert's anatomy, the subtle differences in the primary land, the rake angle, corner reinforcement, and how these define the three main geometry categories.
The geometry choice is really a constant management of a single trade-off. Do you want low cutting forces or do you want high edge security?
Right.
If you need low forces, you use a sharp positive geometry, but it's more delicate, it can chip easily. If you need high edge security, you use a tough reinforced geometry, but it's going to require more power to push through the material.
Okay, let's detail these three categories, L, M, and H. Starting with the lowest force option, the light, or Hadale geometry.
Light geometry is characterized by an extra positive rake angle. This creates the lowest possible cutting forces, making it ideal for the best possible machining conditions. So think pre-machine surfaces, very stable setups, or those very long overhangs on multitask machines where stability is just inherently limited.
And you'd run it with a small depth of cut and lower feed rates.
Exactly. You're prioritizing finish and tool life over raw stock removal.
Okay, next, the versatile middle ground, medium or make M geometry.
This is your general purpose geometry. It balances good edge security with medium cutting forces. It's suitable for most common applications, from medium stock removal to light roughing, basically the average cutting conditions that most shops deal with every day.
So if you're not sure, you start with the innate geometry.
That's the first choice, yeah.
And finally, the beast for high stock removal, heavy or AH geometry.
Heavy geometry features a reinforced cutting edge, often with a large primary land. It prioritizes the highest possible edge security, which makes it perfect for severe, difficult conditions like cutting through heavy cast skin or scale, or performing maximum stock removal on really tough alloys.
And while it requires the highest cutting forces and thus more power, that PC, it ensures the insert won't fail catastrophically when it's facing unpredictable material conditions.
Exactly. It's built to survive.
So even with the perfect L, M, or H geometry, you'll often need a superior final surface finish. And the source details this fascinating technique using specialized inserts designed specifically to smooth the path of the primary cutting inserts.
Yeah, we're talking about wiper inserts. A standard insert, as it rotates and advances, it leaves these tiny cyclical scallops on the surface.
You can feel them with your fingernail.
Right. A wiper insert incorporates an extra long, perfectly flat parallel land, we call it BS2, that trails the main cutting edge. And this land literally wipes away those scallops. It significantly improves the surface finish, and maybe more importantly, it allows the planner to increase the feed rate, VF, while still maintaining a high quality finish, so you boost productivity.
But their application is tricky. There are two crucial mounting rules we need to follow.
Absolutely. Rule 1, they have to be mounted correctly, so you're replacing one of the standard inserts in the cutter body with a wiper. And rule 2, and this is critical, they must be set below the plane of the other standard inserts.
Letter.
Because if the wiper is set proud, if it's sticking out even a tiny bit, it takes the full cutting load. And since it's only designed for smoothing, it will fail instantly and violently chatter the machine.
So the standard inserts do the heavy lifting, and the wiper just comes in for the subsequent, extremely light smoothing pass.
That's the idea.
And to keep that finish pristine, there's a feed limitation.
Yes. The feed per revolution, FN1, must be limited to 60% of that parallel land, BS2, on the wiper. This ensures the long, flat land is effective in wiping the surface clear and preventing the formation of those unacceptable scallops.
Okay, the final major factor in tool selection is pitch, the number of cutting edges. This directly dictates the load on the machine and, critically, the stability of the entire operation.
Yeah, pitch selection is a primary lever for managing vibration. And just like with geometry, we have 3 pitch categories that are tied to the machining environment.
First, coarse pitch, which means fewer inserts.
You select this when your stability is severely limited. Think about our multitask machine constraints again. Long tool overhangs, small machines with limited horsepower, or deep slotting operations where the machine is just inherently struggling. Fewer teeth engaged means less simultaneous load hitting the spindle at once, and that reduces the chances of initiating a harmonic vibration.
Okay, second, close pitch.
This is the default, the general purpose choice. It offers a good balance of productivity and stability, and it's suitable for mixed production on average machines.
And third, extra close pitch.
This is the pursuit of maximum metal removal. It features a high number of inserts for maximum productivity and feed rate, but it is only suitable for the most stable, short shipping materials like cast iron or on massive, rigid machines cutting easy materials. If you try to use an extra close pitch cutter on a long overhang, you will definitely experience chatter.
That brings us back to chatter and harmonics. The Source presents this remarkable, highly engineered solution: the differential pitch cutter. Now, we've established that a coarser pitch helps reduce harmonics. But what does an unevenly spaced tooth configuration actually achieve?
That's a great question. So harmonic vibration, or chatter, is typically generated when the impact frequency of the cutting teeth aligns perfectly with the natural resonant frequency of the spindle or the tool holder or the fixture.
Like pushing a swing at just the right time.
Exactly like that. When all the teeth are spaced evenly, they hit the workpiece and the machine structure at the exact same predictable frequency, which reinforces the chatter.
It builds on itself.
It builds on itself. The differential pitch cutter uses uneven tooth spacing. So this means the vibration amplitude generated by each individual tooth is dispersed across a whole range of frequencies. Instead of one unified, powerful harmonic wave, you get multiple small asynchronous waves.
And that interruption effectively breaks the feedback loop that causes the self-sustaining chatter.
It breaks the loop. And that makes it an invaluable tool for difficult, deep pocket machining or complex setups where just, changing to a coarser pitch isn't enough to solve the problem.
We've saved the most advanced strategic application for last. And it really demonstrates how engineering the cutting force direction allows us to drastically increase productivity. And this involves playing with the cutter's entering angle.
Yes, the entering angle is the mechanism that generates what we call the chip thinning effect.
Chip thinning.
Chip thinning means that by angling the cutting edge relative to the feed direction, we can spread the fretical chip volume over a much longer length of the cutting edge. This allows us to increase the programmed feed per tooth, the FAS, substantially, without actually increasing the maximum chip thickness that the insert itself has to manage.
Okay, let's compare the 3 main angles. First, the standard 90-degree entering angle.
The 90-degree angle, which you find on square shoulder mills, it provides no chip thinning benefit at all. The feed compensation multiplier is just 1.0. Furthermore, and this is critical, the axial cutting forces are high, and they're directed straight downward into the component.
Which makes it challenging for machining thin walls, which are prone to deflecting under that force.
Very challenging.
Okay, next, the balanced 45-degree entering angle.
This is the general purpose champion. It provides that chip thinning effect, which allows for a feed compensation multiplier of 1.41. So you can increase your feed by about 40%. By spreading the force, it also provides reduced vibration, which is particularly important on those long tool overhangs we keep discussing. The force is balanced, being directed at a 45-degree angle into the component.
And this is where the physics gets incredibly aggressive. The 10-degree entering angle, which is the basis of high feed milling.
Right. The 10-degree angle pushes the chip thinning effect to the absolute extreme. It allows for a phenomenal feed compensation multiplier of 5.76. So you can run insane feed rates. But the real mechanical brilliance is the force redirection. Nearly all of the axial cutting force is directed towards the spindle, not down into the workpiece.
Towards the spindle.
Towards the spindle. And this positive stabilizing load on the spindle bearing actually increases the rigidity of the entire machine setup, which is what enables those extremely high feeds and protects thin workpieces from deflection.
So if the force is directed almost entirely toward the spindle, does that mean it alleviates the fixturing requirements for the workpiece itself?
It absolutely does. Since the cutting force is actually stabilizing the machine setup, it's not aggressively trying to lift or deflect the part. So high feed milling is often preferred for parts that are difficult to clamp securely or for very complex component geometries where fixture accessibility is limited. It's a truly strategic force management technique.
Theory is essential, but application is everything. Let's walk through the full cutting data calculation provided in the source material. Let's tie together everything we've learned, from the material's Kc value to the final power consumption. We use the metric values for clarity here.
Okay. So our target is a low alloyed steel, CMC 02.1, and it has a known specific cutting force, a KC1, of 1,700 newtons per square millimeter. The goal is to determine if a machine with a 10 kilowatt capacity can actually handle this operation.
Okay, so the given data is cutting speed, VC, is 225 meters per minute. The cutter diameter, DC, is 125 millimeters. Feed per tooth, FCAV, is 0.21 millimeters. And the number of cutter teeth, ZN, is 5. And the cut dimensions are F here millimeters and AE 85 millimeter.
All right. Step 1, calculate the spindle speed, N. We use that relationship between VC and DC. So N VCAI by 1,000, EDC. Plugging in the numbers, N 225 die 1,000, 3.14 die 125, we arrive at a spindle speed of 575 RPM. That's the first essential program input.
Now, hang on. How did the planner choose that FC equals 0.21 millimeters? That must have come from the insert geometry and the material's own tolerance for shear stress.
Precisely. That FCE value is derived from testing and handbook data for that specific material and the chosen insert geometry, which is likely an NM or maybe an NH, given the stock removal objective. It's the optimal chip thickness the insert can reliably shear off. If we tried to push that SC to, say, 0.40 millimeters, we would instantly risk instability and failure. Okay, step 2, calculate the table feed. VF, using our foundational feed formula and assuming that in this face milling scenario, ZF is close to ZN, VFN, ESC, AZN, so that's 575, NZAC, ECN. The resulting table feed, VF, is 600 millimeters per minute. That's the movement the CNC code dictates.
In step 3, calculate the metal removal rate. Q, this is the measure of our productivity, the volume of material removed per minute. The formula is APA, ECFVF, 1,000, using the depth and width given. Q is C4 by 85 over 600, 1,000. This calculates out to a metal removal rate of 204 cubic centimeters per minute. That's a very solid, high productivity rate.
It is. Which brings us to step 4. Calculate the net power, PC. This is the ultimate validation step. Can the machine actually achieve that 204 cubic centimeters per minute rate? We use the formula linking the metal removal rate to the specific cutting force, PC AEAPA VF by base AC, 60 M106. We plug in our known KC1 of 1,700, so PC 85 by 4 600 as 1,700, 60 N106.
And the resulting net power required is 7.7 kilowatts. So if the machine has a 10 kilowatt spindle rating and a known efficiency of, say, 85%, meaning 8.5 kilowatts is available at the spindle, this operation is perfectly safe and achievable. You've got a comfortable margin for error.
Exactly. But if the machine only had a 7 kilowatt capacity, the entire plan fails. The planner has to go all the way back to the beginning and reduce AP, or A, or VF. That final calculation is the ultimate arbiter of feasibility.
That details calculation really proves that successful milling is an exact balance of so many factors. To wrap up, let's summarize the most critical practical hints the source provides for maximizing stability and efficiency on the shop floor. These are the rules derived from decades of experience.
Okay, first, we have to talk about the stability constraints again. Overhang. Always machine with the shortest possible tool overhang on the spindle. The source provides a serious warning here. Once the overhang exceeds 4 times the tool diameter, 4xd vibration tendencies become severe.
And at that point, simple adjustments are often useless.
They are. You're forced to invest in expensive, specialized, dampened milling tools just to maintain any kind of productivity.
Okay, second hint. Insert choice. When possible, use positive geometry indexable inserts.
Yes. Positive geometry, like our L inserts, provides the smoothest cutting action and demands the lowest net power consumption, the lowest PC. This increases overall tool life, it reduces thermal stress, and it's generally the safest way to achieve stability, especially on those tricky multitask machines.
Third, and a rule we started with way back at the beginning, cutting direction.
We have to reiterate the core rule. Use climb or down, milling whenever possible. You have to leverage that favorable chip thickness formation to minimize friction and avoid work hardening the material surface.
And finally, the most counterintuitive detail, especially for someone who's transitioning from turning or drilling, and that concerns coolant.
Yeah, this one surprises a lot of people. The source notes a profound principle. Only use coolant if it is considered absolutely necessary. Milling is generally performed better without it.
Why is that?
Well, milling is typically an interrupted cut, meaning the insert enters and exits the material rapidly. Introducing coolant can cause thermal shock to the insert, which weakens the carbide matrix and accelerates microcracking and eventually failure.
And it creates a
And it
mess.
creates a mess. The high-speed centrifugal action of the cutter is often the best mechanism for chip evacuation. Introducing coolant can turn dry, easily managed chips into a thick, difficult sludge that interferes with the cut. Unless you're dealing with very specific high-temperature alloys or gummy materials like stainless steel where built-up edge is a problem, stick to dry machining. That is a truly memorable and critical nugget of knowledge.
What a complete technical roadmap we have mapped out today. We started with the theoretical speeds and feeds of the cut, moved through the physics of chip formation and strategic cutter positioning. We dissected the L, M, and H insert geometries, and we finished by calculating the precise spindle speed, feed rate, and that 7.7 kilowatt power requirement needed to achieve 204 cubic centimeters of metal removal every single minute.
It's staggering when you lay it all out, how every single technical detail, from the selection of a vibration-busting differential pitch cutter to the careful calculation of NAC to manage power, it all must align perfectly. These precise mathematical models really reflect the tight tolerances and the high-performance demands of modern manufacturing. Every single choice is a calculated trade-off between maximizing productivity through aggressive feeds and ensuring stability under these demanding machine constraints.
And we've seen how machine flexibility, the rise of turn milling and five-axis capability, demands that the planner become a master of the basics, constantly managing those trade-offs that are just inherent in universal machinery.
So let's leave you with this provocative thought. In the age of the multitask machine, where you are facing these inherent stability challenges like long tool lengths and lower depths of cut, how does the knowledge required from you, the operator or the planner, how does it need to adapt? Does the modern planner simply need to write code, or must they become a dynamic stability manager, using the science of geometry, pitch, and entering angle to actively engineer rigidity into an otherwise flexible, constrained system? That comprehensive knowledge, detailed right here in these sources, is what ensures success when the spindle starts turning.